The following podcast is a proud member of the Blue Collar Roots Network. Find all the shows by visiting bluecollarroots.com.
Now here's your friend who's always full of hot air, cold air, and ventilation air, Bill Spohn.
Welcome back to another edition of the Building HVAC Science Podcast, where we're trying to help create better, more knowledgeable HVAC and building performance technicians. We're trying to help these two professions come together and better understand each other with the ultimate goal of making customers happy in the homes they live in the buildings they work in. And the goal of the Building HVAC Science Podcast, as you might know if you're a subscribing listener, is to help create better, more knowledgeable HVAC and building performance techs. This episode is made possible by myself and Brian Orr, my producer. We have some other trade-oriented podcasts in the Blue Collar Roots Network, and you can find them by going to www.bluecollarroots.com. If you like what you heard today and you've not subscribed, if you like what you're going to hear, I guess you haven't heard it yet, so I'm thinking into the future, which is always very positive. Consider typing Building HVAC Science in the search bar of the Apple Podcast app or an Android, Google Play Music, or Stitcher. You can also listen directly to these podcasts directly in your browser at bluecollarroots.com/building-HVAC science. Now on to the episode. We'll be talking about part 3 of Bill Spohn, myself's AirQuest. We're going to go back and get into the airflow instructionals, some of the podcasts I was doing a little bit before. So to recap, in the last one, I covered the pitot tube and how to select the appropriate manometer for use of the pitot tube. Now let's review some more pressure-related airflow tests, including capture hoods and bolometers. The Truflow Grid, which is a product by the Energy Conservatory, is a pretty awesome patented device. It's actually got U.S. patent number 6439061, which was issued in August of 2002. It's a device made by the Energy Conservatory in Minneapolis, Minnesota. At its heart is a pitot tube array embedded into a panel with holes in it for the air to flow through. Now, the primary use is to measure total system airflow in a residential HVAC or air handling system. The panel itself consists of a solid sheet of transparent plastic with multiple large holes, 12 or 16 depending upon the duct size that you slip it into. Those holes direct streams of air across two tubes arranged in a serpentine pattern. Now, one tube senses the average of all the total pressure points that are the holes in the array opening. The other tube senses the average of all the static pressures, holes, that are in the multiple areas where they're shielded behind the plastic sheet. So imagine this plastic sheet that separates two tubes. One tube is exposed to the airflow, which is the total pressure. The other tubes are exposed to the area behind the airflow, outside of the view of the total pressure and just the static pressure in the duct. So when you properly connect this to a digital manometer, it has the right precision associated with it, just one number, the average velocity pressure of the system shown. Hence, it gives you a bulk measurement. So we were talking before about what I consider bulk measurements. Now, equation was developed by the manufacturer through a lot of research to properly convert these custom velocity pressures into flow, or a flow of cubic feet per minute. Now, the Truflow Grid comes with a slip-on adapters, so it can fit in either the filter slot of most residential air handlers, which allows it to measure total system airflow in CFM. Now, since the air filter must be removed in order for you to insert it into the air handler, the solid parts of the panel simulate the flow resistance of most HVAC filters. But proper use of this grid involves a first step. The first step is very important. That's determining the normal system operating pressure, which is abbreviated NSOP, with a static pressure tip, which actually comes included in the kit. The NSOP number is entered into the manufacturer-provided formula, or if you're using a dual-channel digital manometer from either the Energy Conservatory or Retrotech, the measurements procedure and the formula are built right into the unit. You can dump that NSOP number, normal system operating pressure number, right into the meter. Now, the grid can also be placed at a central return after removing the filter to determine the system airflow. This number can be relied upon as a total system airflow only if the duct system is known to be fairly tight, in other words, fairly leak-free. The beauty of the device is that it quickly averages the airflow across the duct without the need for traversing or scanning to yield just one number or a simple bulk measurement. It does have some operational limits and can only be used on air handlers in the 1 to 5 ton range. The time to take a test with this method can be from 2 to 4 minutes long. Now, to squeeze the best performance from this measuring unit to get its plus or minus 7% accuracy, it's necessary to use a digital manometer with an accuracy of plus or minus 1%. So you got to pick the right manometer to get good results. The time of test is equivalent to all the steps in the temperature rise method, probably even a little bit shorter if you considered all the proper steps we've been talking about lately, and the accuracy that you get from this Truflow Grid is far superior. So the unit comes with 2 calibrated metering plates for different size of return slots, 8 spacers which allow you to modularly configure it to fit the right filter slot opening. These spacers attach to the metering plates and provide for sizing adjustments. It also comes with a static pressure probe for determining that first step, normal system operating pressure. Now, if you choose to use your own fine resolution precision manometer, there are flow conversion tables provided with the unit, which you use to convert the pressure measurements to the flow in cubic feet per minute. In addition to all those other parts that you get with, you also get a decent amount of tubing, which allows you to connect the digital manometer to the Truflow Grid, of course a manual and a carrying case. Now, this kit provides a remarkable amount of convenience, speed, and accuracy for somewhere north of $850. Now, suitable manometer must also be added, and an appropriate digital manometer without calculation can be had for about $450. But if you have a blower door, a duct leakage tester, or a duct blaster, you already have the manometer. Those manometers in those kits have built-in modes to use this device appropriately and directly. Now let's move on to one of the most iconic looking devices in the industry. Somebody should make a little lapel pin that looks like this, the flow hood or the bolometer. One fun fact, the word or term flow hood is actually a registered trademark of Short Ridge Instruments, which is, I believe, out in Phoenix, Arizona. And additionally, the term bolometer with a trademark, which comes from the air balancing ometer, is a registered trademark of Elnor Instruments, which is now part of TSI. So some of those words we flow around or throw around right now, flow hood and bolometer, are actually trademarks of these respective companies. A passive flow hood has a fabric skirt which collects or directs the air flowing from a supply or from a return vent across a sensor that's built into the base of the unit, into the base of the hood. This is another bulk measurement, as I call it, and it simplifies by testing by avoiding the need to traverse the grill or vent or to use any open area calculations. Now, most capture hoods use a pitot tube array, often called a velocity grid. Velocity grids are used in other purposes too, but we'll just talk about the ones that are used in the capture hoods at this point. The grid is placed in the capture zone of a known cross-sectional area that's in the base of the unit. In this way, the capture hood removes the need to calculate the open area of the grill as all the air flows unrestricted, unfettered, and it's directed over this flow grid, and the grid is sitting inside a known area, so the average velocity is multiplied by this area to yield the CFM number. Remember, velocity times cross-sectional area of measurement equals CFM. Well, this device simplifies the measuring process by removing several of the human interfaces, or the human interferences sometimes. These parameters, such as the need to traverse, the need to calculate an open area, the need to average the velocity. Every time you involve a human, sometimes mistakes get made and they multiply, and especially if procedures aren't followed. So this device, a capture hood, flow hood, gives you one bulk measurement, one number, CFM. Now, to improve the measurement quality, some hood manufacturers use straightening arrays that will kill the swirl, kill the turbulence of the incoming airstream. Other manufacturers, like Wire, who makes something called the Smart Hood, actually capture the flow directly from commercial grills. And this is a Smart Hood design, captures flow from commercial grills and splits it immediately, almost right at the face of the grill, into 4 different flow grids rather than channeling it through one flow grid. So it's sort of like divide and conquer. This device has specifically modeled major grill manufacturers to improve the measurement accuracy to 3%. Now, additionally, they have a smartphone controlled predictive balancing method. It's called Predict Air, that can shave 30% or more off the time of doing a commercial balancing job by predicting the optimal flow set points for each register, each grill, in the order in which they should be adjusted. It's really an amazing process. I think there's got to be a video out there on it. It's just a phenomenal kind of thing that uses a lot of great math to help get the work done correctly. There's also a brand new device. It's somewhat of a unique capture hood now. It's available from CPS, called the Easy Hood. It uses a mini vane that rotates at the speed of the air, or at the air velocity speed. It contains a flow straightening grid that's ahead of this mini vane and uses Bluetooth to connect this little mini vane. Really, it fits in the palm of your hand. It connects this Bluetooth device to an app in a smartphone or a tablet. Now, the measurement range, however, on this mini hood, or easy hood, is limited to 1250 CFM. There's also another unique type of hood called a flow finder that uses an internal fan to compensate for any back pressure in the flow caused by covering the grill with the hood. So it's called insertion loss, is what this process is called, when you actually kind of smother the grill and you cause a system effect just by the fact that you're trying to measure it with a capture hood. So this measurement range in this flow hood with its own internal fan, which compensates for the insertion loss, has a measurement range limited to 500 CFM for that device. Most capture hoods have the accuracy in the plus or minus 5% range, and the measurements can be anywhere from 7 to 2500 CFM depending upon the model. So again, there's a good array of choices available for the kind of work that you're doing. Time involved setting up a hood. The easy hood literally can be set up in about 90 seconds. Most other hoods from 3 to 5 minutes to set it up, and they weigh from 5 to 8 pounds. Most of the common ones that we see and use today. And sometimes they actually have additional sensors built into the device to measure things such as air temperature, humidity, and even barometric pressure. So you can get a real comprehensive look at the air that's flowing through the system, as well as measuring the volume flow rate, or cubic feet per minute. The price points of these things I've talked about here for measuring airflow and the capture hood category range anywhere from $400 to $3,300. So it's best to consult with your trusted technical distributor when you're evaluating a purchase of one of these devices. Now let's take a look at hot wire or thermal anemometers. Actually, not taking a look at them, take a listen to them, I guess. Although you can't hear them because a heated wire doesn't really make any noise. A hot wire or thermal anemometer measures the electrical impact, either current change or an amp draw, that's required to keep a heated wire at a specific temperature. Now, through design, extensive engineering design, and calibration in a wind tunnel, this calibrated current allows the meter to determine the airspeed or velocity via the wind chill effect. So the hot wire is actually a bead in the center of a wire that's held across an opening at the tip of the probe on the anemometer. So if you ever look at a hot wire, you should see like a little bulge in the wire. That's the hot wire or the hot bead. So this tiny hot bead only knows the air velocity immediately in the area of the bead. So you're really taking pinpoint measurements with this. Which pinpoint usually sounds like really great, that's a great idea, but you're only measuring air at that one point. So if you have turbulent or chaotic airflow or a lot of variations in the airflow, you're going to need to move this hot bead around to get an idea of the total system airflow, the whole airflow in the area that you're measuring. So this is similar to the narrow opening for the total pressure in a pitot tube. That's why it's pretty much required that you have a multi-point measurement. It means you're somehow traversing the ductwork, and that's critical to obtaining a solid understanding of the airflow by this method. A couple episodes ago I covered traversing in a little bit more detail, so I'm not going to repeat it at this time. In order to improve the measurement, a thermocouple is placed in close proximity to this bead, this heated bead, which is actually the measuring point. The thermocouple measures the temperature of the air that's impacting the bead. The air is a little bit colder than the bead because it isn't being heated by the electrical current. So this thermocouple information is usually extracted and shown on the meter screen. So you also get air temperature as a side parameter that gives you a secondary measurement in most hot wire anemometers. This temperature is used in many meters to compensate for the change in air density due to temperature measurement. I think we talked about air density previously. If not, you'll have to take a look at one of the videos that are on the TruTech site or the HVAC school site. Now, when using hot wire in a turbulent airstream, the measured results can be greatly impacted by the turbulent airflow striking the measurement sensor from multiple directions. So these eddy currents or wind gusts can actually indicate a higher measured value than other airflow measurement methods. This happens in duct types where there's turbulent airflow. This turbulent airflow can even occur at lower velocities, even at very low velocities. That's why there's always this recommendation to move away from any turns or transitions in the ductwork so that the airflow can stabilize and you can get a smooth stream of air that you're trying to measure. Now, to overcome the effect of turbulence, all measurements should be made in a straight section of duct. like we just mentioned, if at all possible. Otherwise, the measurement quality will suffer. Now, an ideal location is in a duct where the upstream transitions, elbows or turns or reducers, are a minimum of 10 diameters before your measuring spot. In other words, upstream of your measuring spot, and at least 4 diameters downstream. The downstream factor comes in because of this thing we talked about a little while ago, insertion loss. You can actually squish air, and a transition can actually push air and have a system effect upstream, and some kind of loss or gain can be created, which isn't what you're really trying to measure. Now, if you can't get 10 diameters before your measuring spot, at least try for 3 duct diameters. So a duct diameter would be, if you're working at a 10-inch cross-sectional area for the duct, 10-inch was one of the duct dimensions, 30 inches upstream. At the very minimum, you try to go 100 inches upstream, which would be just over 8 feet. Also, this airflow should not be interfered with by any dampers. These transitions can cause really odd airflow patterns, and they'll be sensed by the hot wire and actually sensed by almost any in-duct airflow measurement method. So it gets really tricky to measure in duct if you don't have smooth air streams to measure. Now, hot wire anemometers are calibrated to a specific air density, usually a value that's controlled in a lab inside a wind tunnel, and they either require the density to be input into the meter for a correction, or you may have to manually make that correction after the fact. Many hot wire anemometers are calibrated to standard air, which is 68 degrees Fahrenheit, 0% relative humidity, and a barometric pressure of 29.92 millimeters mercury. Almost felt like a weather forecaster saying that right there. Anyway, consult with a distributor or manufacturer of your hot wire anemometer. See if any of these corrections are built in, perhaps built into the meter or built into the app that you're using, or if they're available for you to input. At least be aware that you might have a density change, which would cause a little bit of error in your reading. Now, care must be used when measuring conditioned and turbulent air for this reason. Now, hot wires are not recommended for air velocities exceeding 2,000 feet per minute unless your hot wire is specifically designed for that purpose. There's some very heavy-duty models that can measure airflow in excess of 6,000 feet per minute. That's air velocity in excess of 6,000 feet per minute. You might have noticed we've not discussed the use of a hot wire anemometer to supply a return. Even with a steady hand, a hot wire could be used to traverse the face of return, and that would probably be a return only because of the sort of the lazy airflow that's coming across the sensor and then into the grill. But you must realize that the constriction of the air and any kind of resultant increase in velocity that's happening very close to the front of the grill, that's called a vena contracta. Therefore, you must have a consistent distance away from the face of the return grill in order to make a decent measurement. Now, the use of a hot wire to measure at a supply grill is very tricky. So tricky, I don't really recommend it. The jets of air that are squirting at all odd angles out of this grill opening, the dead zones in front of the grill material, plus the application or perhaps even just estimation of the open area makes this a really difficult process to get a decent CFM measurement using a hot wire thermal anemometer in front of a grill. So just to review this, you must assume you're testing the same density of air that the unit was calibrated in with a hot wire or thermal anemometer. Now, however, for best results, temperature and even humidity and air density, corrections can be built in or input to the meter itself. You must use good measuring techniques, such as avoiding transitions in the ductwork and avoiding measuring supplies. I don't recommend measuring supplies. You must pay attention to the measurement limits, which are usually up to 2,000 feet per minute, and a typical resolution of 1 feet per minute. If you follow all this advice, the resultant measurement accuracy can be plus or minus 5%, sometimes better. Now, this type of test equipment, hot wires, cost from $100, and these would be sort of the smart probes you might see out there that attach to an app, don't have a display or buttons on them, but just they're radio sensors that beam back to an app, up to $250 or more. And the time to set up the test really is seconds, just to turn the device on. The time to take the test itself is minutes, depending upon the size of the duct, the number of traverse points you take, etc. And the resultant measurement you get is the average air velocity, which then must be multiplied by the cross-sectional area of where you made the measurement, and it's usually the open area inside the duct to get the CFM. Thanks for listening to this episode of the Building HVAC Science podcast. If you're interested in becoming a sponsor of this podcast, please email me at bill_spohn, S-P-O-H-N, at bluecollarroots.com. Just as a disclaimer, some of the topics we discuss require technical training for proper interpretation or safe execution. If you're a trained pro, then you can go right ahead. If you're not, please consult with and hire a trained pro. If you're looking for some of the tools or test instruments mentioned in our podcast, take a look at what TrueTech Tools has to offer. That's www.trutechtools.com. You can use the code HVACBS for a nice discount. And that BS stands for Building Science, by the way. And in full disclosure, I'm a co-owner at TrueTech Tools. Wanted to give you one takeaway thought for the day. This is a quote from the famous Evel Knievel. I love the feeling of fresh air in my face and the wind blowing through my hair. If anyone doesn't know Evel Knievel, look the guy up and find out the famous and infamous things that he's done in his life. And that's EVELKNIEVEL. Always, thank you for listening and following us on Building HVAC Science. We do have a Facebook page also where you can keep up with things that we find interesting. If you have any ideas for future episodes, please give me a shout. Send me an email at bill_spohn at bluecollarroots.com. Thanks again for listening. Have a great day.